In this video, I want to give you a few other examples of curves or sequences of curves that are in this sort of staircase paradox scenario. So the staircase paradox is some sequence of curves here in red that are approaching this other curve in green, but the length of the curves in red do not approach the length of the curve in green. In here, the difference is that one approaches 2, the other one is a square root of 2. So let's see some other examples with a little bit of more exciting behavior. For simplicity, in all the examples I'm going to give you here, the limit curve is just the interval from 0 to 1. And then I'm going to give you a sequence of curves in yellow that converge to the interval 0, 1 in different ways. For example, in this case, I'm fixing an arbitrary positive constant k so that the dimensions of each one of those boxes is k divided by n by 1 divided by n. And then the total length of the curve will be 2k plus 1. And since k was arbitrary, the length of the interval is 1, but the length of the curve can be arbitrary and arbitrarily large. We can modify that example so that the height of each box is k divided by the square root of n instead of k divided by n. And in that case, the length of the nth curve in that sequence is 2k times the square root of n plus 1. So the length of the curves is actually going to infinity as n goes to infinity instead of just approaching 1. Now, some people argue erroneously that the origin of the paradox is that in the limit, many points on the yellow curves collapse to the same point in the 0, 1 interval, which is not true. But let's modify this example so it's clear that that is not happening. If instead of squares you use triangles, then the length of that curve is an expression that also goes to infinity as n goes to infinity. Now, other people also argue erroneously that the reason for the difference in length is that the paths in yellow are not differentiable at certain points. So let's smooth those out so that that is not an issue either. If you want to use instead paths that are completely smooth, then you can use 1 over n times sine of 2 pi n x, which is perfectly differentiable for every n between 0 and 1. And it has the property that the limit of the lengths as n goes to infinity goes to a constant, which is not equal to 1. The constant is 4.18, etc., which is a number that depends on pi and the value of some elliptic integral. And I will make a video about how to compute that constant in the future. And the issue here is that even though the nth path here is perfectly differentiable, the limit of the derivatives at any given point as n goes to infinity does not exist for any point between 0 and 1. Because if you fix first n and take the derivative with respect to x, evaluate at a point between 0 and 1, and then let the n value go to infinity, then that limit does not exist. It fluctuates between minus 2 pi and 2 pi, and the limit just does not exist.